Hi everyone. So this lesson corresponds with 2.4, but it's more of a companion piece. Your main lecture on 2.4 has basically all the definitions and stuff you need, but with this lesson I'm going to go over the context of how the different bonds and interactions that were mentioned in chapter 2.3 and 2.4 compare to one another. So this is the most critical slide to get down. So if you need to, pause the video and make sure you have all of this down. If you're doing digital notes, you should definitely make a copy of this image, but then you want to include additional annotations that make sense of this picture. So these are the types of interactions that can be found between two different molecules or two different atoms. A covalent bond is the strongest kind of interaction that we have covered in our class. And when I say interaction, an interaction just means a connection between two molecules or atoms. But in this case, it's actually not just an interaction, it's a bond between two atoms where they share electrons. And it doesn't matter if it's polar or nonpolar, the strength is the same between those two atoms if they're doing a covalent bond. However, the resulting molecule that occurs from polar or nonpolar covalent bonds will result in either charged molecules or uncharged molecules. So any charged substances, which include the results of polar covalent molecules, can create a hydrophilic interaction, meaning a connection between two separate molecules or two separate molecules and ions that are briefly interacting with one another, meaning they connect for a little bit, but then they can separate and make a different connection. But they do make those connections due to their charges attracting to one another. And then if you don't have resulting dipoles because you have nonpolar bonds, then what you end up having is what we call hydrophobic interactions, which are weak, very weak interactions between substances that don't have any charges because they can't really interact with anything else that has charges. So this was mentioned earlier, but remember, a covalent bond is pretty much the strongest kind of interaction and or bond that we've talked about in our class, that we've covered in a class, and it doesn't matter if you're polar or nonpolar, it's the same strength of the connection. So the connection here between these two hydrogens in a nonpolar bond is just as potent and just as strong as the connection here between this hydrogen and oxygen in their polar covalent bond. However, the resulting molecule ends up having either no charges over here, no charged ends, or they end up with significant dipoles, and those dipoles have the potential to create charged interactions in hydrophilic substances, but only when it interacts with a separate molecule or ion. So, in terms of temporary interactions, meaning brief connections that can be made between different molecules or different molecules and ions or other separate atoms, we call those interactions. And what they mean is they can briefly come together, but they can also separate very easily and connect to something else if it offers a similar kind of interaction. So a hydrophobic interaction is the weakest kind of interaction we will cover, and they're made between two separate nonpolar molecules or a nonpolar molecule and an uncharged atom. And uncharged atoms we don't really talk about in our class, but they can include certain metals and other stuff, but mainly we just talked about nonpolar molecules. But in terms of hydrophobic interactions, because they're uncharged, they can briefly interact and hang out with each other without having any issue, but they don't have any charges that allow them to interact with charged substances. Hydrophilic interactions occur between any item with positive or negative charges, whether they're fully charged like an ion or partially charged dipoles that you find in polar molecules, but those charged ends allow them to interact. So an ion will interact with another ion of an opposite charge, but if it's also offered the opportunity to mix it up with a polar covalent substance that has charged ends, it can also do that. The big one, though, is hydrogen bonds. Don't mix it up. So a hydrogen bond is not the same thing as a polar covalent bond. So the polar covalent bond inside this water molecule is very strong and fairly permanent, at least compared to a hydrogen bond. However, because it's a polar covalent bond that includes hydrogen in it, then what it actually does is it makes these dipoles not just partially charged, but super partially charged, meaning they're not quite as strong as an ion's full charge, but they're much stronger in terms of their strength of charge compared to a different polar covalent molecule that doesn't have hydrogen in it. And as a result, its connection that it can make to a different substance that also has the same situation going on, that also has polar covalent bonds with hydrogen, is a little bit stickier, a little bit stronger than a normal hydrophilic interaction. The most common kinds of polar covalent bonds that you will see with hydrogen in it that can form these really good, strong hydrogen bonds are molecules with hydrogen next to oxygen or hydrogen next to nitrogen. I'm going to see a lot of these in the macromolecules that we learn later in this unit. So I want to explain the origins of a hydrogen bond just briefly, but the reason why that hydrogen presence makes it a little bit extra sticky than it otherwise would be is because the thing is hydrogen only has one electron. So the moment its shared electron with oxygen is hanging out with the oxygen, the hydrogen is left without any electrons. So all it has is that pure proton center inside of it that acts as a really strong positive charge. Not quite as strong as a pure ion plus, but pretty dang close. On the other hand, if you look at this other polar covalent bond with nitrogen, nitrogen's electrons are being briefly held by fluorine more often than nitrogen. But even when its electrons, all its shared electrons with the bonded fluorine atoms are with the fluorines that they're hanging out, this nitrogen still has several electrons inside of it that prevent that positive charge that it does have from being quite so pure. So its partial charge isn't quite as potent as would be found on a hydrogen bonded molecule with a polar covalent bond. But basically, just watch out for molecules with hydrogen and oxygen or hydrogen and nitrogen. And if there's two of those molecules involved, whether it's HO or HN, then you're going to get a hydrogen bond potentially between those two separate molecules. So in terms of the strength of attraction and kind of putting hydrophilic interactions within context, when it comes to the strength of the interaction, covalent bonds are basically mostly permanent, whether they're nonpolar or polar, and they're equivalent in strength. However, in terms of temporary interactions, you have two kinds. You have hydrophilic interactions and you have hydrophobic interactions, and hydrogen bonds and ionic bonds are just smaller parts of all potential hydrophobic interactions. Okay, so I'm going to walk you through some examples of various molecules interacting with each other. So I'm going to pick a conventional polar covalent molecule that can't do hydrogen bonds called phosphorus chlorine. I'm going to pick one kind of molecule called nitrogen hydride that can form hydrogen bonds along with water. And I'm also going to talk about chlorine and sodium ions in order to help you get a handle of all potential hydrophilic interactions, meaning charged interactions. So the interaction between the charged end of this chlorine on phosphorus and this nitrogen-hydrogen molecule, this one is still considered just a normal hydrophilic interaction. Any hydrophilic interaction that's sort of like briefly, that's got those charged ends, that's sort of brief, those are considered other hydrophilic interactions, just hydrophilic interactions in general. This interaction between the charged end of this chlorine and this phosphorus is also considered a polar-polar interaction, which would make it a hydrophilic interaction, another charged interaction. And even this interaction between the positive end of the phosphorus connecting to a chlorine ion is also considered a hydrophilic interaction, though it is considered polar ionic. It's still two charged ends interacting with one another. However, these interactions, both between the very, very super dipole end of this hydrogen in the nitrogen bond and this nitrogen in a nitrogen-hydrogen bond, have the capability of making, it is a polar-polar interaction, but because it involves hydrogen, we now say it's extra strong, so it's got extra strength compared to the other one. So it's still a weak interaction compared to a covalent bond, but it's stronger than a general polar-polar interaction. And then this one is what we call a hydrogen bond. As well as this nitrogen, the same nitrogen, if it connected to this hydrogen over here, it would also be considered a hydrogen bond as well. So that's sort of the idea. So I wasn't a big fan of the way I drew that out, but here's another hydrogen bond between the very charged hydrogen on this molecule and the very charged oxygen on the other molecule. Now the interaction between this ion and a hydrogen, even in a hydrogen polar covalently bonded molecule, we'd still classify this, even though it's an ion and a polar molecule, it's still polar ionic, it's still a hydrophilic interaction. It's just sort of other. You compare that to the strength of sodium bonding to a fully charged ion, and then their interaction is very, very strong relative to all of these guys, though still not as strong as the permanency in a covalent bond. But that would be their ionic connection. The way I kind of like to think of these bonds are that a covalent bond, I'm going to use connecting two objects together in a way that's fairly, that kind of illustrates a little bit better. So I consider covalent bonds to be like using super glue to have things stick together. You can bust them apart, but not without a lot of effort and potentially even a little bit of damage. Attaching two ionic things together creates a really strong bond that you can break, but it's kind of tough. So I like to compare it to those super strong magnets, you know, the ones that are really hard to detach from the surface of a fridge or a metal object that's a little bit dangerous to have around your phone. That's an ionic bond. A hydrogen bond is a normal magnet where they will stick to a location, but not that strongly. It's very easy to pull it off. And then other hydrophilic interactions, there's all kinds. Polar ionic would be somewhere between a hydrogen bond and an ionic bond. So, but the most one that we tend to talk about when we talk about other hydrophilic bonds are bonds between polar substances that don't have hydrogen in both. And in this case, their charged ends, they're very lightly charged ends, like the ones you see over here, they are magnetic, but very badly. So I like to think of them as crappy fridge magnets. You know the kind where you're trying to keep a piece of paper on the fridge, and then it slowly slides down the fridge. That kind of magnet. And a hydrophobic interaction is just unstickiness. You rest two objects on top of each other and just hope they don't move. But you're not actively trying to keep them attached together. Sometimes I like to do stupid metaphors, so this is another metaphor I like to use sometimes in terms of relationships. I like to think of covalent bonds as a marriage. They're fairly permanent, but they can be broken up, but it takes a lot of pain, time, and work and effort to get those to happen. And that's what happens when you do chemical reactions. An ionic bond is fairly easy to dissolve with the interference of another substance. So I like to think of them as as long-term dating. Two people dating, they've got to establish relationship, but if one of them starts getting, pulled away by many other objects that they can be attracted to, then they might split apart. I like to think of hydrogen bonds as you're going to be together for a little bit, so it's not insignificant commitment, but it's not for long. So I like to think of it as like an official date. You go out, you get a meal together, you hang out for a while, you get to know each other. On the other hand, polar interaction with no hydrogen, they are interacting but very briefly before connecting with another thing. So I like to think of it as speed dating. And then the hydrophobic people, they're the people with no charges, so no one wants to hang out with them. So they're all kind of sitting on the bench in the corner of the room because no one else will be with them. Just hanging out side by side on the bench, not talking with one another on their phones. Right? Because I mentioned in class, hydrophobic substances don't hang out with each other because they want to. It's just because they don't bring anything to the party. They don't have charges, therefore they can't interact with any other substances with charges. And that's the basic gist of all the relationship between those different types of bonds. This one kind of gives you a good overview of the different relationships I mentioned, but kind of formally. Covalent bonds are the strongest, most stable type of connection. Though with interactions, there's many kinds of interactions, but they are all occur to charges. And hydrogen bonds is a special kind. You do not want to mix it up with covalent bond that occurs between two molecules that happen to have dipoles that contain hydrogen within that polar covalent dipole. And because of that, they have extra charged end that makes them just a little bit stickier than normal polar molecules. Hydrophobic interactions just happen to hang out together because they lack charges, so they can't hang out with anyone else. There was no official new vocabulary. It was just a review of all the vocab we went over before. All right, that's it. Bye.